In the previous class, we learned what are vector spaces, all right. Now, we want to understand what are called vector subspaces, fine. In mathematics, whenever we study some set, we talk of subset of it and try to look at what are the properties which are meaningful for the subsets that we are looking at, fine. Similarly, here, so we are going to look at vector subspaces. We will not be using the word vector again and again, we will just use the word space and subspace, fine. So, let us try to understand this. So, definition. So, let V be a vector space over F, let W be a non-empty subset of V, then W is said to form a subspace of V. So, since I am saying of V, important, F is not allowed to change, F remains the same. I am not allowed to change it, that is one thing. Subspace of V or V over F, you can again use the word over F, if the vector sum and a scalar multiplication in W comes from V itself, all right. So, what I am saying is that when something is a subspace, when something is a vector space, I need to define what is called the sum of the two vectors, fine. Now, W is a subset of V, so every element of W is also an element of V, and therefore, I can just pick all the elements of W, think of them as a vector in V, add the two vectors in V itself and then come back to W, fine. So, again W is a set which is a subset of V. So, every element of W is an element of V itself. So, I can put everything there, add the two vectors in V. What I need is that the sum of two vectors, even though it is an element of V again, it should be an element of W. So, the vector sum has to be an element of W, but I am not allowed to change the definition of sum. The sum has to come from that of V itself. And same thing with a scalar multiplication also. I cannot change my scalar multiplication. Is that okay? So, examples. Fine. I have R2 with me. Fine. In this, I can talk of V or W as, look at all collection alpha times 1 2 alpha belonging to R. I can also talk of W as alpha times 1 0 alpha belonging to R. So, let us see what they are. So, this is nothing but a line in R2 passing through 0 and the vector 1 comma 2. What is this? It is a line in R2 passing through so and so. So, basically it is nothing but the x axis, fine. So, I have some this here, I am not changing the vector addition 1 plus. So, here if I look at 2 0 plus 3 0 is 5 0 for me, all right. Similarly, here if I am looking at 1 2 plus 4 8, then it is indeed equal to 5 10, which is 5 times 1 2, fine. So, I am not allowed to change the addition. Similarly, the scalar multiplication. I can also think of W as R2 itself, the whole set itself, the whole set. I can also take W to be just the 0 vector 0 0 and nothing else. Fine. So, these two examples that I am looking at, where W is the whole set or W is just the 0 vector, these two are called trivial subspaces of R2. Fine. So, in general, start with V, then take W to be V itself or take W to be is equal to just the 0 vector, then they are called trivial subspaces of V, because they do not give us any extra idea. Fine. So, they are important, but at the same time they are not giving us any new idea to us. Fine. So, some more examples. So, I do not know which example it was, anyway 2. In Rn or R3, we can talk of x, y, z belonging to R3 such that x plus y minus z is 0. Fine. I can also talk of, so in R3, I can talk of W is equal to this 3. I can also talk of, so I want to look at R of x, set of all polynomials. Here I can talk of x times px, where px belongs to Rx. Fine. So, here what we are saying is I am looking at only polynomials of degree greater than or equal to 1. Does it make sense? That is the question. All right. So, question. Does it make sense to say Rx, so not Rx, this is the problem. So, in Rx, I am looking at W to say W is a subspace of Rx. Fine. So, if I any two polynomials here, say x px and x qx, where px and qx are polynomial, I can talk of their sum. So, x times px plus qx. So, this is nice. 0 vector is here, 0 vector 0 is or 0 belongs to W, because 0 times x is 0. So, it makes sense for us. All right. There won't be any constants because x is here, everything is getting multiplied by x. So, therefore, there is no problem as such. This may look that we are just doing some things, but what is important is that this corresponds to the idea that we are looking at polynomials which satisfies f of 0 is equal to 0. We are looking at polynomials f of x for which f of 0 is 0. All right. So, 0 is there. All right. All these polynomials have 0 as a root. Fine. Fourth, I can look at, so fix a matrix A, I fix a matrix 1, 2, 3, 4. I look at A equal to this. So, this corresponds to, if I see, I can think of this as x, y, z belonging to R3 such that 1, 1 minus 1 times x, y, z is 0. Fine. I can also talk of A times x, x belonging to R2. All right. I can think of this. Just have a look at it. So, I have a here. So, take any two elements here. So, take B comma C belonging to W. This will imply that B is equal to A x1 and C is equal to A x2 for some x1 x2 belonging to R. and this will imply that B plus C is A times x1 plus x2, and this is again an element of R2. Fine. Is that okay? So therefore, this is again a subspace. 0 vector is there because A times 0 is 0, things like that. Fine. I can also talk of set of, so I can talk of all matrices, say M3 of R as is there. I can define W for me as all matrices A belonging to M3 of R such that trace of A is 0. I can also talk of this as all A belonging to M3 of R such that A11 plus A21 is 0 and things like that. I can talk of that. All of them will be vector spaces. Fine. Now, what is not a subspace? That is more important, not a subspace. So, in R2, let us look at some examples. So, look at define W as all xy belonging to R2 such that x and y are greater than or equal to 0. Fine. So, I am looking at the set which is this. Fine. This is the set that I am looking at. So, in this set if I look at, so this is my x, this is my y axis. If I look at this set, all right. So, R2 is a vector space over R or over scalars, some scalar. Scalars always contain negative numbers. So, now if I take alpha to be negative, alpha negative, and look at alpha times xy, which by definition is alpha x, alpha y, that is the definition in definition of scalar multiplication in R2, then alpha x is less than or equal to 0, alpha y is less than or equal to 0, and therefore, I am in this part. All right. So, I am changing. So, even though I am multiplying, these two elements are supposed to be an element of W, but this part need not be an element of W. So, W is not a subspace. Is that okay? So, not a subspace. Fine. Similarly, if I take W is equal to all xy belonging to R2 so that x is equal to y plus 2, all right, not a subspace. Why it is not a subspace? Because note that the vector 0, 0 does not belong to W, or if I take two elements, say x1, y1, x2, y2 belonging to W, then this implies that x1 is equal to y1 plus 2, x2 is equal to y2 plus 2. So, now if I add it, I get x1 plus x2 is equal to y1 plus y2 plus 4, all right. But for vector, for W to be a subspace, what we need is their sum should be there. So, their sum is nothing but x1 plus x2, y1 plus y2, and therefore, what I require that x1 plus x2 should have been y1 plus y2 plus 2. Fine. But here I am getting 4. So, this is not a subspace. Similarly, you can show that W is equal to all xy belonging to R2 such that x is equal to y square is not a subspace. Fine. So, there are restrictions to being a subspace, that is very important. You need to understand that there are lots and lots of restrictions for getting a subspace. Fine. There are also differences over complex numbers, but I will not get into that part for the time being. I will move to the next idea, what is called the linear span. Linear span of vectors. All right. So, what we want is that, so let us look at ideas that I am talking about. Suppose I have two vectors, say 1 0 and 1 2 in R2. Fine. Idea to get the largest possible subspace of R2 which contains vectors of the form alpha times 1 0, beta times 1 2 for alpha beta belonging to R and their sums. Is that okay? So, understand what I want. So, given any collection of vectors, I am allowed to multiply by scalars whatever I want. I am allowed to multiply by scalars. I want that collection to be inside that set itself, whatever set I am looking at. I also want that I should be able to add this new collection, all right. So, from two vectors I will have countable number of vectors because of alpha and beta being allowed to take any real number. So, there will be uncountable number of them. So, I have now a huge collection. For example, this collection is going to give me whole of x axis. This is going to give me collection of all the points on the line which passes through 0 0 and 1 2. So, the line containing these 2 points. What I want is that I should be able to add those vectors also. Is that okay? So, I want the largest possible subspace which contains vectors of the form this. I am not saying that I want the biggest. I want only those vectors which have this form. Is that okay? That is very, very important. Or I want, so this is the way one can think of it, one way. The other way to think of is that in place of 2, now let me take 3 of them, 1 0 0 and say 0 1 0 in R3, or let me take previous one itself, 1 2 0 itself, fine. So, I want to get largest subspace of R3 which contains vectors of the form alpha times 1 0 0 plus beta times 1 2 0 and alpha beta belongs to R, fine. This is one way of understanding the largest part. I want the also which should correspond to a smallest subspace of R3 which contains the vectors 1 0 0 and 1 2 0. Is that okay? Here I am talking of a smallest subspace, here I am talking of the largest subspace. So, please understand it, they are very important concept. What is called the linear span of a vector space? We write it as, the notation for that is LS, all right. So, here I am looking at LS of 1 0 1 2, here I am looking at LS of 1 0 0 and 1 2 0, fine. Sometimes I may just write LS of 1 0 0 1 2 0, fine. But as I said, we want to look at only vectors as column vectors. So, this is the right one, but in a hurry or sometimes I will just write this to save a space for us, all right. So, sometimes you need to save a space and therefore, I will use this, but that is the notation part. So, these are notations, all right, notations for linear span. Is that okay? So, understand it, linear span means I want the largest subspace which has this form, at the same time it is a smallest subspace which contains 1 0 0 and 1 2 0, fine. So, understand. Now, if I am saying that 1 0 0 is there, so I am saying that 1 0 0 belongs to a subspace, all right. What does it mean? Subspace means 0 vector has to be there, If x is there, y is there, then x plus y has to be there. Fine. If x is there, alpha is a scalar, then alpha times x has to be there. So once I am saying that 1 0 0 is there, it means that 2 0 0 is there, 3 0 0 is there. Fine. Alpha times 1 0 0 is there. So it implies that I need x axis is in subspace. Whatever subspace I am looking at, whatever this subspace is, what I want is, since 1 0 0 is there, therefore x axis has to be there in that. Fine. Similarly, 1 2 0 is there. Fine. Since 1 2 0 is there in the subspace, it means what? This implies that, and 0 is already there in that. So 0 and this, if I look at these two, I can look at their linear combinations, or I can say that alpha times 1 2 0 is there. So alpha times 1 2 0 is there. So 1 2 0 times alpha basically gives me the line passing through 0 0 0 and 1 2 0. So this line is also there for you. So I have got two lines, x axis and this line, and what it says is that if I have a subspace, sum of any two vectors is also in that. So an element from here and an element from there has to be there. Any element here is of the type alpha 0 0. Any element here is the type beta 2 beta 0. So therefore what I get here is their sum will give me alpha plus beta 2 beta and 0. So this has to be there with me. So you can see that from one point of view, this part gives you this part, and this, the smallest part, tells you that I cannot go beyond this, cannot go beyond. Fine. So linear span basically means trying to understand things here. Fine. So this is important for you, that you need to understand what the linear span means. So for example, that itself, so the linear span of, so let me take two vectors 1 1 1 and 1 2 3. What is the linear span of this? Let us try to compute this. So the definition tells me that this is of the type alpha times 1 1 1 plus beta times 1 2 3, where alpha and beta, they are real numbers. Fine. So we are saying that this is the linear combination. So this word is used, but I am not yet said what is the linear combination. I want to look at collection of all vectors of this type. Fine. So what we are saying is that, so in terms of system of equations, what I want is system of equations. All right. So this, if I look at, this is nothing but some vector x y z belonging to R3 with some properties. What is this property that we need to find out? All right. It has got three components. So therefore I have x y z. So what I have is I have got alpha times 1 1 1 plus beta times 1 2 3. I want to find what this sum looks like. So in general it has three components, but what exactly does it look like? So let us go back to the system of equation and try to understand this. What it tells me is that I want to generate, so looking at all possible values of x y z belonging to R3 such that, all right, such that a star has a solution. Why I am saying has a solution? Basically because we are giving values to alpha and beta, or we are saying that look at the system 1 1 1 1 2 3, alpha and beta are unknowns, and I have vector here, say b1 b2 b3. Fine. So I am looking at this, and what I want is, so look at the system that Ax is equal to b has a solution for every b. All right. So here I am saying that I want to look at the system Ax is equal to b. what is given to me is that it has a solution. So, want to find B such that Ax is equal to B always has a solution. Fine. So, when I am saying they want to find B such that Ax is equal to B always has a solution, it means that, recall that this matrix which is B1, B2, B3, I do not know what they are, and this matrix 1, 1, 1, 1, 2, 3, they should have the same rank. So, let us look at it again. Want to find a B, alright, want to find a B such that Ax is equal to B always has a solution. Since the word always has a solution has come, it means that rank of the coefficient matrix should be equal to rank of the augmented matrix. So, let us look at the rank of the augmented matrix. Fine. So, what we want here is 1, 1, B1, subtract it, 1 minus 1 is 0, 2 minus 1 is 1, here it is B2 minus B1, I hope I am doing correctly, 1 minus 1 is 0, 3 minus 1 is 2, B3 minus B1, at the next stage it is 1, 1 B1, 0, 1 B2 minus B1, or 0, 0 B3 minus B1 minus 2 times B2 minus B1, which gives me B3 minus 2 B2 plus B1. All right. So, what we see is that augmented matrix rank is same as the rank of the coefficient matrix only when B3 minus 2 B2 plus B1 is 0. All right. Fine. So, that is, this entry has to be 0 for us. Fine. So, what we are saying is that this system has a solution, always has a solution, always has a solution, has a solution if B1, B2, B3 satisfy B1 minus 2 B2 plus B3 is 0. All right. So, now if I relate these two ideas here in terms of x, y, z, what we are saying here is that x minus 2y plus z should be 0. So, I would like you to check here, look at this vector 1, 1, 1, I get 1 minus 2 times 1 plus 1, which is 2 minus 2, which is 0. Let us look at this part again. X is 1, minus 2 times y is 2, and z is 3, which is 3 plus 1 is 4 minus 4, which is 0. So, both these vectors, they indeed belong to this. Fine. So, what we are saying is, this is the way to write the linear span, that is the definition. This is called the algebraic way of writing it, algebraic way, fine, and this is called the geometric way, geometric way, so that we are able to say it what plane it represents. This is a plane, so recall that this is a plane containing the vectors 0, 0, 0, 1, 1, 1 and 1, 2, 3. Fine. Again note, I am writing it in terms of row vector itself, basically because I do not have much space. Fine. So, I will be interchanging these notations, row and column notations, but be clear that I will be using only, when the theory comes, it will be only the column vectors that are interested or that are important for me. Is that okay? So, this was what I am saying is that when I am talking of linear span of some things, it means that I am looking at a plane or some space which contains those vectors. All right. So, I am looking at the smallest plane, the smallest plane containing those vectors, and the 0 vector. So, 0 vector I am not putting here in general, but I want 0 vector should always be there because I am talking of a subspace. Subspace means 0 has to be there. All right. I am not proving here that linear span of any system is a vector subspace, but I have given you an example to show here that whenever I have got a linear span of certain set of vectors v1, v2, vk, then this is a subspace, and not only that, it is the smallest subspace containing the vectors v1, v2, vk and the 0 vector. Is that okay? So keep track of that. In the next class, we will build up in these ideas further. All right. Thank you.